This is AQA A-Level Chemistry, and we're now on part 7 of the energetics topic. And in this, we're going to look at an alternative way of drawing out Hess cycles, but the majority of the video is going to be built around the final calculation, and that's going to be bond enthalpies and mean bond enthalpies. As always, I'm going to recommend that you pause as you go, trying each activity, and then review and see how you've done. So in the first instance, a few questions to get you started. And hopefully you've very quickly seen that this question has got a very simple answer. That in every single case here, the enthalpy of formation will be 0 kilojoules per mole. And that's because following the enthalpy of formation definition, the enthalpy change when 1 mole of a substance is formed from its elements in their standard states under standard conditions, all of these, there would be no change at all. Now, in terms of how you explain that, you can simply say by definition. And just as an additional note here, no question, but just to point out, quite an important fact about carbon graphite having its own state symbol. Just something to watch out for. Okay, we're going to take a look at thermochemical cycles. Now, this is an alternative way of drawing out a Hess cycle. So we've got all of the figures here. I've put them into the highlighted yellow, and this was a question that we went through in more depth on the previous video when we were looking at enthalpy of combustion data calculations. But in a thermochemical cycle, as we can see, the arrows are vertical, they point up or down, and the arrow will tell us whether it's exothermic, that will be a downward arrow, or endothermic, an upward arrow. So how could we rearrange this Hess cycle into a thermochemical cycle? Well, let's start, because all three of them are negative, with the biggest negative, and that's going from our 2C, 3H2 and half O2 to the 2CO2 and 3H2O. And that's a downward arrow, as you can see. And I'm going to put the value on. Now, in terms of the alternative route, where we have got our formation of ethanol, and then the ethanol being combusted to carbon dioxide and water, I can put those figures in there. But we're going to move on to the main thrust of this final video. We need to know what we mean by mean bond enthalpy. It's a good opportunity, though, to think about bond dissociation enthalpies and bond formation enthalpies. So have a think about these questions. And hopefully you are remembering that bond breaking is an endothermic process. What would be similar and what would be different if we were making a bond rather than breaking? Well, I think it's really important, and you'll see as we go through some examples here, that the magnitude is the same, that the bond energy will always have that same value. However, for an exothermic and an endothermic reaction, the difference will be the sign we give it. Exothermic will be a negative value and endothermic a positive. That's going to be of huge importance when we look at the final calculation in a couple of minutes' time. Have a think about this question now. And we do need to consider that when we have Cl2, that is a bond dissociation enthalpy, whereas a CH bond, we would tend to talk in terms of a mean bond enthalpy. And the reason is this, that chlorine only exists in one environment. If I have a chlorine bonded to another chlorine, I don't have anything else bonded. But actually, a CH bond can exist in a range of alkanes, but also in alkenes, in alcohols, in aldehydes, in ketones, in carboxylic acids, in esters, etc. And in every single different compound, there will be a very slightly different CH bond enthalpy. And so when we talk about the mean bond enthalpy, that's taken as an average over a range of different compounds. Quick summary here of some of the key details before we go back to the calculation. And I'm going to put all of the answers up at once here, because we've already spoken about it. Breaking bonds is endo, that's a positive value. Making bonds is exo, that's a negative value. So now let's move on to the bond dissociation calculations that you will probably find familiar from GCSE. So have a go at this question. And there are different ways of setting out the answer. I always tend to do it in this way. I take my bonds broken, and I've got 4 CHs, and I've got 2 O double bond Os. So I've got a total of 2736. That's plus 2736 because we're breaking all of those bonds. Bond breaking is endothermic, endothermic is positive. And the bonds that we're forming, I've got 2 C double bond O bonds, and I've got 4 OHs. That takes me to a total of negative 3460. Now, the overall delta H for this reaction is now going to be the sum of those two values. So 2736 take away 3460, giving me a value of negative 724 kilojoules per mole. So let's try this one. And this is a relatively straightforward one. We are breaking one HH and one ClCl, and we're forming 2 HCl bonds. So now let's put the figures in. The HH is 436, that's positive. The Cl is 243, that's also positive, because bond breaking is always positive. But for the HCl, it's 2 times negative 452, because the magnitude is the same, but the sign has changed because we're making the bond. Now I can do the calculations. My total for bonds broken is plus 679. My total for bonds formed is negative 904. If I add those together, I get a value of negative 225 kilojoules per mole. So let's take a look at another example. And in this case, I am breaking 6 NH bonds. I'm forming 1 N triple bond N bond and 3 HH bonds. So I put those figures in, 6 times 391. That gives me a total of plus 2346 for all bonds broken. And for bonds formed, I've got 1 negative 946 and 3 negative 436s, a total of negative 2254 for all of the bonds formed. I then add those two numbers together. Delta H is 2346. Take away 2254, giving me a value of negative 92 kilojoules per mole. Another example. One big thing to watch out for here, and if you do fall into this trap, there is no harm in actually sketching out the display formula, because in C3H8 there are only 2 CC bonds. But from there you can see the rest of them: 2 CCs, 8 CHs, 5 O double bond O bonds, and I'm forming 6 C double bond O bonds and 8 OH bonds. You can probably see why sketching out the display formula there could be helpful. Certainly as you get to bigger molecules, I do recommend it. Let's put all of the figures in. And then from there, let's work out my total energy for bonds broken, which is plus 6666. And my total energy released for bonds formed is negative 8528. Now, if I add those two numbers together, I get 1862. But because the overall change is negative, it's negative 1862. And that sign could make a difference of 1 or 2 marks within the calculation. Slightly different calculation here for you to try. Have a go and see how you do. So the equation itself is just good practice. And now let's look at bonds broken and bonds formed. In propene, I'm breaking a CC bond, a C double bond C bond, 6 CH bonds, and I'm breaking 1 BR-BR bond. But I'm forming in the dibromoethane 2 CCs, 6 CHs, and 2 CBRs. Now, as I put the figures in, you can see we have a slight difference in how we've tackled these previous calculations, because we're calculating the bond enthalpy for BR-BR. So I've got all of the rest of them. I put those in. I do the same for the bond formed. And from there, I'm going to follow the calculation through, but instead of x equals, I'm taking my negative 95 as the overall change. I've got my 3432, which is the addition of 348, 612 and 2472. I've got my negative 3720, which is negative 696, negative 2472 and negative 552. And I've got my x, which is my unknown BR-BR bond. Now, if I rearrange to make X the subject, I then see that X has a bond dissociation enthalpy of plus 193 kilojoules per mole. That takes us to the end of this video, and it takes us to the end of this topic. Thank you for listening. Goodbye.